So I'm just going to have you guys do just a little bit of review and something that's not too difficult. But tomorrow and the next day we'll really close up the whole chapter. These are just kind of a few skills you'll need for that. But our ultimate goal here is, again, finding these roots, intercepts, solutions, whatever you want to call them, exactly without doing a table and without doing a graph. So similar to everything else we've done before, is that we don't want to have to make a graph or a table just to find these out. So that's where we're leading to. Alright, so here we go. Alright, so this first way I'm going to tell you is that we're going to always follow these steps. Find if there's a GCF, look for difference of squares, cubes, factoring, grouping. We're going to try all these first, and then if nothing else works, tomorrow I'm going to show you a way to use synthetic division to really speed things along. But for now, for today, we're still just going to practice the first three. Okay, and the last one will be, yeah, it's a method that always works, but it just takes the longest. So we want to be really good at these three. You don't want to be one of those people during a test that says, well, this is too long. I still have, like, 4 problems left. If you try to do everything quadratic formula with, back in that last test, you wouldn't finish. And same thing here. If you try to do everything with synthetic division, there's just too many numbers to test and for trial and error, and you won't finish. So we want to be good with these methods before we go any further. So looking at this, what would be the first step? So always look for a GCF. Where's the GCF here? That's just x. Yeah, just x. Nothing more than just x. Okay, these are equal to 0. So when we get it to something that we can solve, usually a first power or second power, we can just solve it easily. If it's just by itself, it's going to be equal to 0. Anytime you get a GCF, that GCF is going to be a solution of 0. And this one, pretty straightforward to solve. We have subtract 2 on both sides, and then take the square root. And what do you get? X equals what? Plus or minus I root 2. Okay. Good. So what's the degree of this function? What's the degree of this function? 3. Yeah, degree just means highest exponent. How many solutions are there? 3. 1. And then the plus is 2. The minus is 3. So the degree should match the number of solutions you have. Always matches. And the plus or minus counts as 2. So this is why if you say the answer is just I root 2 and you forget the plus or minus, that means you have 2 out of 3 roots written down. And the third one's kind of like a gimme. You just have to put the plus minus sign. You don't have to do any extra work. So let's not forget about that. So that's just one basic example for how to use the GCF. Always look for it. Once you take a GCF out, it's a lot easier. The next one is a good example of, there's no GCF, but we have to remember all our difference of squares, difference of cubes, and sum of cubes formulas. Just to review, a squared minus b squared equals what? A minus b, a plus b. And we had a cubed minus b cubed. What did that equal? A minus b, a squared, plus ab, plus b squared. So remember that these were the same. These were opposite, and this was always positive. Okay? And the same thing worked with the sum of cubes. Same thing worked with sum of cubes. Same acronym works. So after doing a GCF, you want to see if any of this stuff can be applied. Because, yeah, we could do it the long way. You know, we could throw it into a process that I'll tell you about tomorrow. It's kind of long. It works all the time, but it's kind of long. But if we can do this, it'll be a lot faster. So on this one, go down here. Which one can you use here? I can rewrite this as a difference of two squares. So as long as I can write it as two things being squared, x squared, squared, and 4 squared, so that's a difference of squares. And what's another hint that this is a difference of squares? The number is a perfect square. It's 16. If you see 16, 25, 36, 49, any of those numbers, it's kind of a hint. If you see 8, 27, 64, 125, it's kind of a hint it's a perfect cube. So, yeah, use the context clues there to help you decide what to do. Alright, so we have x squared minus 4 and x squared plus 4. This equals 0. We're going to, instead of graphing this whole thing, and it probably looks something like, you know, like this, some sort of W shape, right? Instead of doing all this work to graph it, we can get these x-intercepts, you know, without all that work. So we have x squared minus 4 equals 0, and x squared plus 4 equals 0. Solve each one. X squared equals 4, x equals plus or minus 2. Yeah. How many roots should there be total? 4. Yeah, it's a 4th degree. So we should have a total of 4 answers altogether before we're finished. And then x squared equals negative 4, so answer is plus or minus 2i. Okay. So yeah, 1, 2, 3, 4 roots total. Got all 4 of them. And of course, we might need to do some factoring, grouping if there's 4 terms. That's how you know if you use grouping, if there's 4 terms. Factoring, I'll give you an example in a moment. Okay, good. Anything else? That's good. Okay. Now, part 2 for your homework is just going to basically do this in reverse, believe it or not. So the question here gives you the equation. You're supposed to come up with the roots. What if I gave you the roots? I told you the roots are plus or minus 2 and plus or minus 2i. Could you come up with x to the 4th minus 16? Okay. Just work backwards. Okay. Work the whole thing backwards. Okay. And that's a lot, actually pretty easy compared to working this direction is more difficult because you have to figure out, well, how does it break apart? But if you already have the roots, okay, like here, I just have the roots here, like 30, yeah, I'll do 34. If I have the roots, it's simply this. I'm going to have 4 binomials, 1 for each root. And they all start with x. And for each one, you just plug in the opposite of what they give you. So actually, when you, for negative 2, you're going to plug in positive 2. And for positive 2, you're going to plug in a negative 2. For positive 4, negative 4, positive 6, negative 6. And then just spend the time to multiply all that together. And that's, after you multiply it all together, there are 4 roots, right? And once you multiply all these together, there'll be an x to a 4th. So, and there could be a good way of multiplying things together, like a plus 2 and minus 2. You know, if you know that, oh, that's another difference of squares. So that's going to be x squared minus 4. Just for those two. And then these, you can multiply these together. That's x squared. Add them up. It's 10x. Multiply them. 24. And then maybe at this point go ahead and do a box and multiply it all out to get the final polynomial. I highly recommend multiplying 2 of them together and then 2 of them together and multiplying those 2 together, as opposed to take this answer and multiply it by x minus 4 and then take that answer and multiply by x minus 6. It's a little bit more lengthy. Alright. Do we have time? Yeah, we actually have time, so we can go ahead and do this. So, I'm going to use a box. Again, I prefer the box. You can always use distributive property, but I prefer the box because all the like terms are lined up diagonally. So x squared times x squared, x to the 4th. Set that up for you. X squared times negative 4 is negative 4x squared. X squared times negative 10x is negative 10x to the 3rd. X squared times 24 is 24x squared. And negative 4 times negative 10x is positive 40x to the 3rd. And negative 4 times 24 should be negative 96. Just 40x. Okay, thank you. Just 40x. Good. Okay, so we have x to the 4th. Yeah, I forgot that since this skips degrees, it goes from x squared to the 4th. Looks like our like terms don't actually line up. So we get negative 4x squared, 24x squared. Give you, yep. And then plus 40x, and then minus 96. So again, not difficult. Yeah, it takes a little bit of time, but it's not something we should say, I don't know what to do. If there's a mistake, it's going to be on, well, write neat, be clear, not so much like a calculation or something. Alright, so that's an example. These are all real roots. And so what happens if there's an imaginary number like a 4i, or a complex number like a 1 plus 2i? Okay. Well, we have to think back a little bit. That imaginary and complex number comes in how many at a time? How many do you get at a time when you get imaginary numbers? Did you ever get one imaginary root? No, you always got a plus or minus. You always got pairs of imaginaries and complex. So on these, you need a little bit more information. If they say 4i, you have to know that there's another root there, negative 4i. So this is really a 4th degree polynomial. They're just giving you the most basic information you need. They're saying, well, if I put 4i, you better know that these only come in pairs, so you have to know that negative 4i is also a root. Yep. And same thing here, if like this complex one, a 1 plus 2i, you have to know that 1 minus 2i is also a root. So this is a third degree. So you never have a single, or I have 3, you never have a single imaginary answer or 3 complex answers. It's always, there's 0, there's 2 imaginaries, there's 4 imaginaries, there's 6 imaginaries. Impossible to have an odd number of imaginary or complex roots. So just that's that one little thing, and then from that point on, it's like everything else. Like 35, you'd have to do x minus 4i for this one, and then I'd probably do this one next and do x plus 4i, and then x minus 3 and x plus 3. Once again, it's probably easier to multiply the imaginaries together and multiply these two together, and the answers from those two multiply together. So like on this one, you get x squared plus 16 minus, but then the I times I is negative 1. So yeah, think of if we were doing this backwards, don't write this down. If this is equal to 0, what would we do? We would get x squared equals negative 16, take the square root of both sides, we get 4 plus or minus 4i. So remember, we're just doing the backwards of this. So and this one would be x squared minus 9. And then those two, we'll have to do a box and to find out what our 4th degree polynomial is. Yeah, you'll notice that whenever you had x squared plus a number, that's when you got imaginaries. So when you multiply the imaginaries together, you should see, yeah, plus. As opposed to when they actually factored, there's always a minus. So you'll see a lot of patterns, things that kind of fall together. 36, how many roots does 36 have? Yeah, 2i, 3i, 1. What others? Negative 2i and negative 3i. So again, they're always in pairs. So this is going to be, your final answer on this is going to be x to the 5th, something else after it. Okay. The conjugates are a little bit different. Okay, so just to set up for 37, we have x minus 9. And then, remember I said it's x, it's going to be minus, it's going to look a little weird, 1 plus 2i. And x minus 1 minus 2i. And then multiply, do the work on this, multiply them together. Alright, good. So these will take a little bit longer, but doable as long as we remembered our I squared is equal to negative 1. We use our boxes, right neat. Okay. Anything else? I think that was it. Tomorrow we'll go into the equivalent of the discriminant for quadratics. I'll give you something that's, sometimes useful. I won't lie, it's not useful many times. But it'll let you know by looking at the signs how many real positives, how many real negatives, and how many imaginary roots there are. So it's kind of like the discriminant. It lets you know the possible number. That's the only drawback. It doesn't actually tell you exactly how many there are, but it say, oh, it could be 2 or it could be 4. That kind of thing. Alright, yep, guess we're all done. So hopefully I'll see you tomorrow if I feel well enough. And
If not, send a movie with